Authorship attribution, the task of identifying who wrote a given document, has long been a cornerstone of forensic linguistics, legal investigations, and literary scholarship. From Lorenzo Valla's 15th-century dissection of the donation of Constantine to the Unabomber case, the ability to trace authorship has had profound real-world impact. Today, with the rise of large language models, we're witnessing a renaissance in this field, not just in theory but in practice. But here's the challenge. Modern authorship attribution isn't just about matching style. It's about doing so across genres. Imagine a political news article as your query, a document about policy, structure, and argumentation. Now, your candidate is a Stack Overflow post discussing literary theory. They're worlds apart in topic, tone, and structure. Yet the true author may be the same. The system must ignore topical cues and instead detect subtle, consistent linguistic patterns, the fingerprints of style. This is the essence of cross-genre authorship attribution. Identifying an author when the query and candidate differ not only in topic, but in genre, format, and even intended audience. Until now, most systems have relied on a single-stage retrieval approach, a one-shot comparison between documents. But in large-scale settings, where tens of thousands of candidates exist, such systems struggle with both accuracy and efficiency. Enter the retrieve-and-rerank framework, a two-stage pipeline long used in information retrieval, now adapted for authorship analysis. In this video, we'll walk through the first system to successfully deploy LLM-powered retrieve-and-rerank for cross-genre authorship attribution. We call it SADIRI-V2, and it sets a new benchmark, outperforming the previous state-of-the-art by 22.3 and 34.4 absolute success at 8 points on HIATUS's HRS1 and HRS2 benchmarks. Let's break down how it works. Hash the two-stage pipeline. The pipeline begins with a retriever, a fast, efficient model that narrows down the candidate pool from tens of thousands to a manageable top 100. We use a bi-encoder architecture, where each document is independently encoded into a vector representation using a large language model. These vectors are then compared via dot product to estimate authorship similarity. But here's the twist. Unlike traditional IR, where the goal is to match documents on topic, we must train this retriever to ignore content. To do that, we use a supervised contrastive loss. The model learns to push documents by the same author closer together, and those by different authors farther apart. Crucially, we don't just use random negatives. We apply a hard negative mining strategy inspired by SADIRI. We cluster documents by semantic similarity, then ensure that each training batch includes documents that are similar but not by the same author. These become hard negatives, the kind that challenge the model to learn true authorial distinctions, not just topical ones. But the real breakthrough comes in the reranker. Why the reranker is a game changer. The retriever is fast, but it's not perfect. It may miss the correct document in the top 8, though it often ranks it within the top 100. That's where the reranker comes in. The reranker is a cross-encoder, a model that jointly encodes the query and candidate document as a single input. This allows it to capture fine-grained, context-aware features that a bi-encoder can't. It's more accurate, but also more computationally expensive. So we only apply it to the top 100 candidates retrieved earlier. But here's the critical insight. Training this reranker is fundamentally different from training an IR reranker. In information retrieval, negatives are typically selected based on their similarity to the query, documents that are close in content, but irrelevant. But in authorship attribution, that approach backfires. Why? Because in our cross-genre setting, the positive document, the one written by the same author, is deliberately chosen to be topically dissimilar to the query. So if you train the reranker using only negatives that are similar to the query, you're teaching it to reject documents that are semantically close to the query, even if they're the true match. This creates a perverse optimization. The model learns to score high only documents that are far from the query, not because they're the same author, but because they're different topic. In fact, we found that training on query-similar negatives alone worsens performance. The reranker scores below the retriever. So what works? We introduce a targeted data curation strategy for the reranker. We sample negatives from 3 distinct categories. 1. NDQ, documents close to the query but not the same author. 2. ND+, documents close to the positive document, same author, different genre. 3. NR, random documents with no particular connection to either. By sampling uniformly across all 3, we force the model to learn robust authorial features that are invariant to topic. It learns to recognize the author not by what they write about, but how they write, their syntactic habits, lexical preferences, sentence structure, and rhythm. And the results? A 6.2-point absolute gain in success at 8 on HRS1 and 8.5 points on HRS2, a massive improvement over the retriever alone. The role of large language models. We didn't stop at fine-tuning Roberta. We leveraged decoder-only LLMs, QN3 and Mistral-Nemo, as both retriever and reranker backbones. Why? Because LLMs have a deeper understanding of language structure, semantics, and style than smaller models. But training them is expensive. So we use LoRA, low-rank adaptation, a parameter-efficient fine-tuning method that only updates a small fraction of the model's weights. This reduces memory usage and training time significantly. We also introduce a memory-efficient clustering mechanism using random projection. Since full document embeddings from LLMs don't fit in GPU memory, we project them into lower dimensions while preserving cosine similarity, a technique grounded in the Johnson-Lindenstrass lemma. This allows us to maintain hard negative sampling at scale. And the scaling effect. Clear. As we move from 0.6B to 12B parameter models, performance improves steadily. The 12B Mistral-Nemo model achieves 42.1% success at 8 on HRS1, a 16.1-point gain over the previous state-of-the-art. Why this matters? This isn't just a technical improvement. It's a paradigm shift. For decades, authorship analysis has been constrained by the assumption that style and content are inseparable. But SADIRI-V2 proves that with the right training data, model architecture, and loss function, we can decouple style from substance. We can now build systems that don't just match topics. They recognize authors across genres, formats, and even domains. And that has real-world implications. From identifying anonymous whistleblowers in leaked documents, to tracing the origin of disinformation campaigns, to protecting privacy by detecting authorship without exposing content. This work opens new doors. Final thoughts. SADIRI-V2 demonstrates that the retrieve-and-rerank framework, long a staple of IR, can be powerfully repurposed for authorship attribution. But it also shows that simply adapting IR techniques isn't enough. In cross-genre settings, the training data must be curated with care. The reranker must be trained on a balanced mix of negatives, not just those near the query, but those near the positive and those that are truly random. And above all, we must stop assuming that LLMs are just good at matching topics. They can learn to detect authorship, but only when we guide them to look beyond content. This is not the end of the journey. Larger models, better negative sampling strategies, and more diverse training data will push the boundaries further. But for now, SADIRI-V2 stands as a milestone, a system that doesn't just guess who wrote a document, but understands the author behind it. And that's the future of authorship attribution.